So it's really a wonderful opportunity to get a chance to talk about this essential problem that's coming to the forefront in an interesting way. And finally, chemical oceanography is becoming kind of cool. And it's a wonderful moment for chemical oceanographers. So what I wanted to show you here is the carbon cycle, kind of what's central to everything. And this is where it's coming and going, and the reservoirs. I don't really care if you notice the actual values. What I want you to think about, see at first, is that most of these fluxes or exchanges are about equal. So there aren't really big offsets, and that's how nature likes to work. Generally, it's in balance. So you can add up 60 and 60 and 1.6 and get 121.6. It's 121.3 there. So that there's some sense of balance there, and nature is in fact in balance. And there's one part here that is not in balance, and you've got us taking carbon out of the ground and putting it into the atmosphere, and that's the problem here. So you've already seen this a little bit. We're going to rely on a few of the similar things. This is CO2 going up, and it's related to the temperature going up. That's, of course, what we've been hearing about for the past several decades, is this greenhouse effect that we're going to get increased temperature. And that's happening, and it's going to happen more. It's really captivating to the community to figure out how much the temperature is going to go up. And that's a tremendously interesting problem that will take a long time to figure out. But we're doing an experiment right now. We're increasing CO2. And as one of our colleagues says, this is a planetary experiment that we're embarking on that's probably not a moral experiment. But we're going to figure out how temperature and CO2 correlate. That's, of course, not what we're dealing with now. What we're talking about today is that this CO2 will not only increase temperature, but it will change the chemistry of the ocean. And one of the beautiful things about the ocean is that it's soaking up all the CO2. So the CO2 is going into the atmosphere, and these are the emissions of carbon, of CO2. That's how much is going into the atmosphere, and that red line there is the average amount that's actually that's staying in the atmosphere. So what's fantastic about the ocean is it's sucking up or soaking up about half of the CO2, which is wonderful. Otherwise, it would be in worse shape than we are now in terms of atmospheric CO2. So about half, more or less, of the carbon dioxide is going into the ocean. This is not really very good news for the ocean, of course. The ocean already has a tremendous amount of carbon already. I'm going to toggle back to this. You notice that these units, these are fluxes, but this is the total amount. Notice the ocean here has 38,000 of these units. The ocean has a tremendous amount of this carbon, and that's what's being denoted here. It's mainly as bicarbonate and carbonate, and I don't want to turn you all into chemical oceanographers, but basically what's going on is that we've got some CO2, and we're combining it with water, and we're forming, and again, I apologize if you didn't like chemistry, but this is a very simple reaction here, and we're forming this H2CO3, which is carbonic acid. And so the minute you hear acid, you can think, yeah, the oceans are becoming more acidic, we're forming this acid. It in fact doesn't stick around as this carbonic acid because that's not stable. It's going to use some jargon here, it's going to dissociate into a proton hydrogen plus this bicarbonate. And about 90% of the carbon in the ocean is that bicarbonate here. So we have the carbonic acid, it kind of, it dissociates, it forms this H plus, the proton, and some bicarbonate. That's mainly what the ocean is there. That's mainly what's there, and there's your acid. There's your increase in acidity, your decrease in pH. And so when we all get together, we get really concerned about that. And that's what we're talking about here, that increase in acidity. So this is an acid-base reaction. We've got the acid, and it's being buffered by the base, forming that bicarbonate here. And this is what is mostly in the ocean. So we've got some buffered reaction there. And that's what the ocean is doing. It's neutralizing the acid. And this is wonderful news if you care about what's going on in the atmosphere. And in the long term, if you care about millions of years, this is also very good because actually we're buffering the CO2 that's going into the atmosphere. The oceans are a tremendous asset. But in the medium term, we're increasing the acidity of the ocean, which is really bad news for critters that live there. So what I'm trying to give you a sense here is that the oceans have a tremendous amount of carbon, huge amount of carbon. They're sucking up a lot of, or absorbing a lot of the CO2 from the atmosphere, and eventually it'll all be neutralized. So in the very long term, we're all happy, but in 100,000 millennial timescales, we get a little concerned. And that's where the corals come in. What we're looking at here, I am not going to teach you what this Greek letter means, but basically everything over about 3.2 or so, everything over this, we're going to form coral, or form calcium carbonate, which is what coral is made out of. And it's aragonite, if you care. And everything below this, coral doesn't form. So the author here has made a clear distinction between yellow and blue. And so here we are in pre-industrial times. The world's a happy place from a coralline perspective. It's actually light blue. Here we are today, darker blue, but corals are still able to form. And I'm going to skip right to, I'm sorry, this is amount of CO2 in the atmosphere. 280, 380, 450. I don't care about units. These are parts per million. 500, you see at about 500 and 550 ppm. Things start really getting bad for the coral. And once we get to 650 ppm, you can see that coral isn't going to form easily. It's not going to form at all. The corals just can't make a living. They can't make their shell. What's so important about this from a policy perspective is this gives us a clear limit for CO2 in the atmosphere that we haven't been able to get at before. It's unclear how much CO2 is going to increase in the atmosphere over the next 100 years. And that's what we're trying to figure out. What's the upper limit? And so if you care about coral, the upper limit is about 550 parts per million. And this is a very useful number. Below 1 is when coral dissolves. And as a chemist, I'm not a biologist, as a chemist, this is what I get interested in, because actually that coral, the aragonite, the solid, starts dissolving, and this is really bad news. This is the same picture that you saw before. These are really images that help you associate these values of CO2 with what the coral might look like. So here we are in present day, or maybe last year's value. You see pretty fish and pretty coral. 380 odd ppm, a little change, increase in temperature. And then once we start increasing the amount of CO2 in the atmosphere, you can see that things look a little bleaker. I'm going to remind you where that is in this space. We're here. So at about 500, 550 ppm, it starts getting kind of bleak. And then over 500 ppm, the coral really aren't able to make a living. This is a much lower limit than many policy folks were thinking and talking about. We've been talking about doubling CO2 for decades now. What happens if we double CO2? And we're way below doubling CO2. I'm going to toggle beyond, show some pretty pictures that you've seen before. This is the organism that's so important. And it's so important because it's down here in the Southern Ocean. It's the base of the food chain in the Southern Ocean, which is what Chris was talking about. And the minute you eliminate this, it's hard to know what's going to happen because these are the base of the food chain. This is what things rely on in the Southern Ocean.